Good morning and welcome to CTS 120. My name is John Armke. I will be your instructor for this semester, and we're going to go ahead and start with a bit of a soft lecture, if you will, on the appendix for your textbook. The reason I feel like Appendix A in particular is very important is because it covers safety. And when you come into the lab and you're doing different procedures here with me on campus, it's going to be critical that you understand that there are certain safety aspects that may not necessarily be immediately intuitive to you, things that may not necessarily pick up as being necessary, or even something that would cross your mind to watch out for. So we're going to talk about a little bit of that and a little bit of the mechanics behind why certain things are dangerous. We're also going to discuss some environmental concerns. So you guys are probably very aware that there is a lot of electronics about. People have a lot of different materials, so of course we have to be aware of where are these materials going when they are no longer quote-unquote useful, when they're no longer able to perform their respective duties just because they've aged out or they've been damaged. So first things first, we're going to talk about some measures and properties of electricity. So electricity, of course, being the big danger whenever you're working with electronic equipment. You know, by itself, unpowered, usually it's not too dangerous unless it's very large, and then of course there's danger of things falling. But electricity, once equipment is energized, has several different components that make it dangerous to human beings. As we are biomechanical machines in our construction, there are things that electricity does to us in certain quantities does to us in certain quantities that is detrimental, potentially dangerous. So the first thing we're going to talk about is the volt, represented by the letter V. This measures electrical force, so the amount of energy transitioning. If there's a measurable amount, then of course we have force. You can think of it almost also as pressure, the amount of oomph behind an electrical flow. So the power supply, in our example here, we'll go ahead and take the voltage that comes out of the wall, 115 is the traditional house voltage, and then makes it usable by internal components to the computer. So 3.3, 5, and 12 volts being the most common. Those are the ones I want you to worry about. If you want to see another example of this kind of step down occurring, you can look at something much smaller, which would be a power transformer for your cell phone charger, if you will. If you look on usually the bottom side where the plug plate is or things like that, you may see a sticker that talks about what the amperage is and what the voltage is. And essentially what this is doing is taking the 115 that comes out of the wall and converting it into something usable by your particular device. Something that's a bit more high powered may need more amperage, voltage, or wattage. Okay, and usually those higher numbers are reflected on the charge block, which is why, for example, if you were to take a charger for an iPhone, it may not have enough power to charge an iPad, especially if it is a newer iPad and uses a bit more energy to run, so something like an iPad Pro. Next, we have the amp, or ampere, represented by the letter A, and this is going to measure current or flow through a system from one point to another in a given period of time. So an LCD monitor requires 5 amps to operate, a small laser printer requires 2 amps, and an optical drive uses 1 amp. Essentially, think of it, and we'll visit this analogy again several times. Think of electricity like water flowing through a garden hose. If you constrict the amount of aperture, the opening at the end of the hose, the water flows with greater vigor. It's faster because the amount of force behind it is consistent. Water is incompressible. You can't crush it through pressure. That's what hydraulics operate on. But it can move faster in order to keep the same volume moving across an area at the same time. Resistance is the constriction of that opening. So if we cinch down the opening of a particular spigot or aperture or whatever else, then the resistance of that constriction is measured in what we call ohms. Ohms are traditionally represented by the Greek letter omega, usually the capital. Most of these are going to be represented in capitals. So resistance is just the tendency of a material to not allow the flow of electrons to occur easily. That's what electricity is. It's movement of electrons through a substance. Especially they refer to metals as like a sea of electrons, which is why metal allows electricity to flow very easily. So something like rubber would have a very poor conductivity, very high level of resistance. Human flesh has a surprisingly high level of resistance, unless of course it is wet or covered in an electrolyte solution such as salt, in which case the conductivity changes quite a bit, which we'll talk about in a moment. Traditionally, wires and cables in a computer are made with things like copper, or in some cases like contacts on the end of a connector may be made of gold, in which case these will have a high resistance to corrosion and will have a resistance of near 0 ohms. There are, of course, what we call perfect conductors that can be created in lab conditions, but perfect, of course, is always in quotation marks. The joule, represented as the letter J, is a measure of work. Now, work, if you remember from physics, is force applied over a distance. So in this case, we are registering the amount of work that is needed to push, to push 1 amp of electricity, 1 amp of current through 1 ohm of resistance. So a surge suppressor, for instance, that you would find in a power strip is going to be rated in joules and describes the work that it takes before the protection fails. So you can almost think of it like a roller coaster. You have a situation where you're kind of climbing up the hill, that tick, 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 and that's building up potential energy, right? So there comes a point where if you were to essentially stop cranking the cars up the hill, it would just kind of sit in place because it just kind of sits against the ratchet catch on the drive for the chain drive. But once you hit the top of the coaster, there is an equilibrium point where gravity is then able to take over and you rush down the hill. There's no acceleration required because gravity is taking all of that potential energy that was stored up and converting it to active work, kinetic energy that is being expressed. So think of it that way. Think of it as a joule rating, let's say 500 joules, as being the top of the hill. And you have a spike that hits at 300 joules. Well, boop, it goes up to that mark, but it does not tip over. It just sits there. And then it can be, ratcheted back down. Or you have one that's 400. Well, that's still within the protection range, so that spikes up, and then it walks its way back down. If you have something, however, that is 505 or 510 joules, just keeping it in comfortable numbers. The second you clear that tipping point, all of a sudden the inertia of that surge breaks the protection circuit. And then all of the cars, if there is more surge behind it, will basically push forward as gravity drags it forward. So that tipping point basically is when the circuit breaker, what we call, trips. Tripping a circuit breaker is when you pass the point at which its joule rating is able to sustain protection. A watt is represented by the letter W, and it is a measure of power. And when I say a measure of power, I don't mean like strength, I mean power consumption. So the power needed to operate a device. An LCD monitor, just an average one, might be rated somewhere around 14 watts. Depending on the monitor, you may have a really, you may have a high resolution monitor. You may have one that is a particularly large size. You may have one that uses slightly different display technology, uses something like OLED as opposed to just standard LED or LCD. Couple of different options that would be there, but there is still power consumed per cycle in order to sustain the operation of that device. A DVD burner, example of something that uses a bit more power, would be using around 25 watts while it is burning a disc. If we're talking about a Blu-ray player, that's probably going to be a little bit more power because, again, that has to control slightly more sophisticated machinery. CD player would probably be a lot less because it's not using a burning laser, it's using a reading laser. So the CD player, just being a reader, is able to use a lot less. The function of what it's doing is almost a measure of the exertion required to do something. If you pick up a really, really heavy box and you haul it up a flight of stairs, you're going to feel that fatigue, that amount of power consumption, if you will, a lot more pointedly than you would if you were just saying, oh, I forgot my keys, let me jog back upstairs, and you're not carrying anything. So these are just some scientific explanations of the things that I just gave you some rough rundowns of. So voltage is the difference in electrical potential between 2 points. This is equal to the work done per unit charge, usually a coulomb, done against a static field of resistance. So a coulomb of charge across 1 volt of electric potential is 1 joule of work. So we see that these units are interrelated. The amp is a flow of electrical energy over a surface, and that's a quantitative measurement given as 1 coulomb per second. So we've got some different damage thresholds here. These damage thresholds are based on the fact that your heart and your respiratory system operate on what's called autonomic function. There are subsystems of your brain that constantly make sure that your heart beats, and that if you are not actively controlling your diaphragm through conscious movement, that you will breathe on your own. So 10 milliamps, the victim essentially is unable to let go of whatever surface they may be holding that is energized. Basically, the 10 milliamps is enough to override the nerve impulses that your brain produces to say, open your hand, to let go. Okay. 20 milliamps, breathing becomes difficult, and this is because the diaphragm in your abdomen that pulls up and down in order to inflate and deflate your lungs is being overridden at that point. The 20 milliamp is able to reach the trunk of your body and affect your breathing. It's difficult to do, but you can still do it. At 75 milliamps, the diaphragm becomes paralyzed and breathing stops. Okay, so this is a very scary point at which you can't breathe, you can't oxygenate your blood, and in order to preserve executive functions and things like that, your brain will actually cause you to lose consciousness to try and keep autonomic functions running normally. Now, that is not to say that once you pass out that you start breathing normally again. It just means that in an attempt to get you away from whatever it is that's damaging you, your body will automatically shut down. At 100 milliamps, we get to a very dangerous area of what we call ventricular fibrillation. For those of you who have studied anatomy and physiology or know something about the heart, you know the heart has 4 chambers, 2 pairs, the atria and the ventricles. The atrium, the top of your heart muscle, contracts at a different rate than the ventricles at the bottom. Now the ventricles receive, like if you're talking about the circulation from the arteries to a vein to be reoxygenated, the atrium takes blood in from the returning artery, compresses it and squeezes it into the ventricle. The ventricle being at the bottom is where blood pools. It relies on gravity to kind of do its work. And then when it contracts, it forces from one side to the other. Ventricle passes from one to the other. And then the ventricle on the other side is able to pass blood, forcing it up against gravity into the second atria to return it to the, I believe, the superior vena cava, which would then start circulating it against the lungs to be able to oxygenate it and pass it back into the body. So again, it's been a little while since A&P. I apologize. I'm trying to give you just a rough idea. But the ventricles are very, very important because they have to compress against gravity to be able to force blood through the lower chambers of your heart. Now, when we have what's called a fibrillation, this is where you have a spasm, if you will. The electricity is causing the heart muscle, the cardiac muscle, in your ventricles to twitch and seize to where it cannot squeeze in order to pump blood against gravity. It doesn't have enough strength, and that will, if not removed, kill you very quickly, in fact, because it requires what's called defibrillation. I'm sure you've seen that in medical shows, of reintroduction of a very strong electrical charge to reinstantiate what we call confluency, to where the heart muscle will regain consistent contraction and release across its surface. So 100 milliamps is a very dangerous exposure point. 200 plus milliamps is very, very dangerous for other reasons, but it causes what's called cardiac clamping. So this is actually an area in which you could possibly survive that kind of damage because your heart doesn't sit there and spasm and twitch, and instead performs what's called cardiac clamping, which is where the entire heart muscle seizes like a fist and holds in place. Now, because we're not having spasmodic changes to the surface of the cardiac muscle, we're not damaging the heart muscle's ability to maintain a consistent pulsation. It can then, once the current is removed, be able to release and constrict under normal circumstances again. Now, you may have damaged heart muscle due to the extreme amperage, but it's not going to be quite the same. That's how, linesmen and people who have experienced lightning strikes have the ability to survive even though they're having more electricity pass through them in that discharge moment than if they were to like grab onto a transformer on a power pole, things like that. Really, really extreme stuff. And that's why I always tell people, voltage hurts, amperage kills. Because voltage it's very disruptive. There's potential for tissue damage and things like that. But amperage is what will start messing with your organs, especially your heart, your brain, your lungs. The ohm, the measure of resistance, our protection against electricity in this way, is measured based on where the contact occurs and where the level of moisture at our skin may be in a given time. So imagine that you are fresh out of the shower. You're actually in a bit of a better situation than you would be in most other cases because other than the fact that water has impurities in it and you generally don't bathe in distilled water, most of the salt, dirt, and other suspended materials that would be highly conductive have been removed. Now, because you are wet, you are going to have a higher level of conductivity than you would be dry, but most of the surface salt and things like that have been washed away. So again, it's all conditional. So let's say you get out of the shower, you're completely dry after you towel off, and then you get dressed, and somehow you touch a live surface. You're going to have a very low level of resistance because your flesh is going to be dry, and most of the salt, oil, and dirt has been removed in most cases. Now, if, however, you were working out and you were in a gym or something like that and a power surge occurred, because you're covered in sweat, you would actually be very conductive because there's a lot of salt and things like that that are on your skin. Good thing is because electricity likes to take the path of least resistance, it will try and stay on the surface rather than passing into deeper tissues. Which is kind of like how if you have a power line that touches a car, the tires are actually grounding the car to the earth, so the metal skin is dangerous, but inside the car you would still be safe. Again, it doesn't try and find a complicated path or try and penetrate, it just tries to find the quickest space to where the energy buildup in a particular flow can discharge. So between your ears, the internal resistance, not including your skin, is only about 100 ohms, and this is because the fatty content of your brain and things like that has to be able to have a high level of conductivity, what we call hyperosmosis, to be able to transfer neural energy back and forth between synapses. From your hand to your foot, it's closer to about 500 ohms. So if you were to grab a line with your hand and then discharge and ground through your foot, that would be a resistance of about half a kilo ohm. And then from about 1 kilo ohm up to 500 kilo ohms, half of a giga ohm, is the difference in resistance between wet and dry tissue. So the ohm is a very interesting form of measurement. The joule is where we have energy transferred when a force of 1 Newton is applied over 1 meter, yielding 1 Newton meter. In a surge protector, we talked about the roller coaster ramp. So that's how much the energy the protector can absorb before it fails. So anything beyond that protection limit is basically attacking things directly. So instead of attacking, a line of defense, it's attacking the primary component that we would try to protect. Watts are used to quantify the rate of energy transfer in a system or power consumption, as I said. Derived as 1 joule per second. This is when an object's velocity is held constant at 1 meter per second against a constant opposing force of 1 Newton, and it generates 1 watt per cycle. So if we're talking about per second, as we have here, 1 meter per second against 1 Newton generates 1 watt. Now, when we're talking about electrical current that we deal with in our daily lives, we generally talk about what's called house current. That is what we consider to be AC, alternating current. Oscillates rather than using a unidirectional path. It flips back and forth from a positive to negative 115 volt value 60 times per second traditionally. So if you think about your refrigerator or a fan or things that make kind of that humming sound whenever the motor is running, that is what's called a 60 cycle hum. It's a very common thing. It's a noise that I'm sure you're well aware of. If you're in a room that's otherwise quiet and you can hear kind of the buzz of the fluorescent light bulbs above you. If you listen in the background of this recording, I don't know how well you can hear it, but there is a fan. It's just kind of that, that's about 60 hertz. So that's interesting thing about that noise that most people know without knowing, sort of thing. Voltage is going to flip back and forth, and this actually allows it to travel over long distances with fewer repeaters and things of that nature. But when you get to a house and a component needs to consume that electricity, then we have to transform it, well, actually we have to rectify it into a direct current source. So we use a rectifier to convert from AC to DC. And the way I often remember that is just RAD, RAD, rectifier, AC, DC. You could also, if you're more musically inclined, a rectifier is a part of a guitar amplifier and a kind of an amplified setup, if you will, and then AC/DC, of course, being a very famous Australian rock band. The inverter inverts what the rectifier has done. So rectifier traditionally means to correct. So you hear that rect syllable that is shared. So to rectify means to correct or to straighten, to take off of a deviating path. So to rectify something is to take it from oscillation or vacillating back and forth and making it a single trip, a single direction, a single focus. Taking a curve and making it into a vector value, if you will. The inverter flips that around, and it says we're going to go from a DC component to an AC component. So this may be where maybe you're pumping a lot of DC into something, and you only want to make sure that it uses the electricity that it needs but does not overconsume. So any bleed over in the system, if you will, can be converted back into AC and possibly fed into another device or back to the original power station. The transformer is going to change the ratio of voltage to current while keeping power constant. So the amount of wattage that is being passed into a device or across a given set of transmission is going to say, okay, we need more voltage, less current. We're going to do that transformation there, or we're going to do less voltage, more current. We need it to flow faster. We can do that as well. So these are just some circuit diagrams, probably something you won't need to worry about unless you're in electrical engineering. Transformer, same thing. Just wanted to show you a little bit of what these logic diagrams look like. Something I want you guys to be aware of, again, this is not something I'm going to test you on. Most of what is in this chapter is not something I'm going to directly test you on. It is stuff that I just want you to be aware of so that way you can protect yourself in the lab environment. Ohm's Law. This pyramid is probably very familiar to any of you who got through high school science. The text of it reads, the current through a conductor between 2 points is directly proportional to the voltage across those 2 points. So current, the amount of flow, if you will, is proportional to the voltage from one point to the next. So we have to figure out the resistance. So V is equal to I times R. The voltage of the equation is equal to the amperage multiplied by its resistance. From this law, we derive a couple of things. we say that if V is equal to I times R, then I is equal to V over R, and R is equal to V over I. There's a commutative property that we use from algebra. Power is equal to V times I, which is equal to V squared over R. I apologize for the lack of superscript on the, what do you call it? On the V squared that should be there for power. Same thing for resistance. V squared over P, or P over I squared for resistance. Voltage is equal to the square root of P times R, and amperage is equal to the square root of P over R. Now, why do we need to know this stuff? You know, we're not electrical engineers in this particular class. Well, it's nice to know, because if we ever have to figure out the power consumption of a particular component, or whether or not a system would be stable at a particular configuration, these are things that we know. And then, of course, dealing with overclocking for CPUs, which we talk about later. These are all helpful calculations to have on hand. So again, this is a shorthand, this is a primer. You never know where you're going to use this stuff. I didn't when I first started learning. So again, as I told you a little bit ago, a couple slides back, think of electricity as being analogous to the flow of water through a pipe. If we have a constant amount of water moving through the pipe, because water is incompressible, and we constrict the diameter, which is what the ohm is doing in the graphic here on the left, the pressure behind that flow must increase. So in order to move the same amount of material through a given area, and it's being constricted from one point to another, pressure must increase from point A to point B in order to maintain consistent delivery of volume. This is it's just a graphical representation I made here in PowerPoint for an electrical outlet. And I color-coded it to help you understand the relationship between the neutral, hot, and ground lines of the material. So the hot line is the connection we use to go from the power station to the building. So that's the delivery. We use the hot line in order to bring electricity to a particular location. The neutral line is the return. So the hot line is the delivery, the neutral line is the white one. So that's the one where we pass power back to the power station from being consumed, if that is the case. That's how we complete our circuit. And then the green is the ground line. The ground line is attached to a conductor mounted into the ground. Remember how I talked about a lightning strike, and how lightning looks for the quickest path to be able to discharge its energy from one place to another. So if we have electrical energy being discharged through a lightning strike, power surge, etc., we want it to find its way from wherever it's originating to the ground as soon as possible. So most buildings have a metal infrastructure, if only cabling or things like that, that are connected to a metal spike driven into the ground where that electricity can then be dispersed. So the ground line allows us to individually anchor every socket that is connected to our power grid for a particular building or series of buildings, and ensure that that shortest path is always provided for, so we don't have any places where the current pools or eddies and causes damage. Be aware of your surroundings in the workspace. How do we protect ourselves? We've talked about, of course, several dangers and gotten kind of deep into the physics of it, but quote unquote deep. But how do we make sure that we're not leaving ourselves open to potential hazards? Well, being aware, of course, is a big one. Keep a clean workspace. Remove any jewelry. Things, of course, with metal contact would be higher levels of conductivity than your skin. Tie back long hair if you have it. If you're in possession of a big beard, sometimes hairnets can be helpful. Think of it the same way as if you were working in food service. You don't want stuff getting in the way. If you have a tie that you're wearing, wear a tie clip. If you have a scarf, you may want to go ahead and remove that. If you have a lanyard with a name badge or things like that, you don't want that kind of clacking around in the way, so go ahead and get that into a more secure location. Power down your system and unplug it, and then do what's called a discharge of the system before opening the case. Now, number one, we want to try and ground the system wherever possible, and I'll show you guys that in the lab a little bit more effectively. We have a what's called an anti-static mat, which is kind of this tan, spongy mat that is made out of an anti-static material. It helps to ground the chassis that you're working with, so that you can clip to it with a little metal alligator clip, and it connects to a button that's mounted into the mat itself. Discharging the system means that once the power down process has occurred and we've unplugged it, we press and hold the power switch on the front of the case for about 3 to 5 seconds. And what this does is it tries to push it through the startup process. Obviously, if your system is not plugged in, it will try and fail to process that particular activity. And what this does is it removes any potential capacitive charge that still remains in the power supply. I'll give you an example here. I have Frankensteined my computers together pretty much my whole life. You know, if I have a friend that's getting rid of an old box, or, you know, oh, my video card crapped out, so you know, I'm going to go ahead and do the insurance claim, and it's like, oh, well, they're going to give me some new RAM as well or something. I'll take old RAM, I'll take old video cards, old power supplies. Long story short, I came across a 1,000-watt server power supply. It's kind of old, you know, 2 or 3 years comparatively. And I slapped it into the box that I had at the time, and it was probably triple what my system needed at the time, thereabouts. We'll talk about the 30% rule when we actually get to that chapter. But the thing is that if I was ever going to work on my system, I had to make sure I discharged my case, because it would actually spin enough power to where it got to the BIOS screen for my machine. You know, it actually would start to boot up, and then it would finally lose enough power, just because for that little flicker of time, it had 3 times as much energy, or 2.5 times as much energy as it actually needed. So expelling that allowed it to get a little bit farther than most people would expect. A lot of the time when you do the discharge, you press the button and it just flickers. You know, the light flares up and then it goes away. Mine went a little bit farther than that. So we always want to be sure we're aware of that kind of thing whenever we're working on different systems. Electrical fires. This is an interesting thing, because we're probably only going to really deal with Class Cs in our work, but it is important to know that there are several different types of extinguishers out there. Class A is a water-based extinguisher that is used with wood, paper, things like that. It's used with textile materials to try and suppress what we call a standard fire. Class B is a petroleum-based fire suppressant, which is going to be usually CO2 or a chemical foam. This is used with gasoline, kerosene, benzene, oil, anything made from crude petroleum. This is because the volatility and energetic nature of this material makes it much harder to put out. Something else is that if you were to try and use water on a petroleum-based fire, you would create what are called micelles. If you're into skincare, or if you have a child, or if you've worked with these things at all, you've sometimes heard of what's called micellar water or micellar wipes. And this is water that has been mixed with a very specific balance of oil. And this is because of the chemistry principle, like dissolves like. If you want to remove Sharpie from a material, you need to use rubbing alcohol, because the ink that is in a Sharpie is suspended in alcohol. So in order to clean something, you want to use the same kind of material it was constructed from. You know, you have to find a way to deal with it chemically. So if we have these micelles formed, essentially these little bitty beads of oil and water, what this does is increases the surface area of exposure to whatever is burning. So that means that if we have water, which would normally flash into steam at a certain exposure to temperatures in a fire. You know, temperature of a fire is usually about 550 to 600 degrees starting, and then it goes up from there depending on accelerants. The flash point into steam is much, much lower than that, so it's very easy to turn water into steam by getting it onto a fire. That's why you hear that hiss. Everything's kind of condensing, or I'm sorry, not condensing, vaporizing. If you do that with oil, because oil likes to form very similar in biology to what we call a lipid bilayer, it takes these little bitty pockets of water and spreads them out, and it gives them just enough insulation to where they don't flash vaporize. But what they do is they start to boil, which means that they fling the oil that surrounds them outwards into a cloud. And that atomized petroleum then is able to burn much more effectively because there's oxygen mixing all around it. And that's where you get that big ka-woomph fireball thing that you've seen. I'm sure if you look up videos on the internet of water on an oil fire or anything like that, you'll see that it accelerates very aggressively because essentially you've increased the exposed surface area of that particular material. Class C fires, these are electrical fires, so this is started from an electrical source. The reason that we have to use what are called non-conductive chemicals is because if the lines that are on fire are energized, we do not want to provide a pathway for the electricity to move to us, to the extinguisher, or to the area around the fire until the lines can be de-energized and the fire can be put out. We want to make sure that we're not using water, which again with its impurities can be used as a conductive material, and then certain types of CO2 foam, depending on what the foam substrate is, can be conductive as well. So we have to make sure that for electrical fires we use a Class C. Now there are combination extinguishers we may see in these first three classes, where maybe you have an ABC or a BC extinguisher. Those are perfectly fine. Just make sure that the class of fire you're dealing with, textile-based, petroleum-based, or electrical-based, is being supported by the extinguisher you wish to use. And it's the pass method. It's the pull the pin, aim the nozzle, squeeze the trigger, and sweep at the base of the fire. You want to make sure that you're not trying to do it from the top. You want to try and cut it off at the base. You're not trying to suppress flames that are in midair. So, if you're going to work with electricity in high quantities, or if you're going to work in a shop like that, especially things that are very sensitive to fire, make sure you're aware of what the fire suppression program is in your particular organization. Class D and K, honestly, I include it because they're kind of cool. If you ever watch them being used, they're really, really neat. Class D is usually sodium carbonate. It's a dry powder extinguisher that's used to break up combustible metals. So for those of you who are fans of Mythbusters, you may have seen things like magnesium, titanium, thermite, types of iron oxide that are oxidized in different ways. This stuff is very energetic and traditionally burns so hot that not only does it instantly atomize water, vaporizes it right away, but it is a chemical reaction that is occurring. There's a reducing agent and an oxidizing agent that is causing this energetic release that we call fire, that we have to break the chemical drivetrain that makes that happen. So usually the sodium is a very reactive substance and will bind to those combustible metals and form different compounds to try and keep them from continuing to burn. Class K, this is where we use very alkaline chemical foam sprays in order to saponify fats and oils into inert soapy foam. So this would be things like using lye or similar material, LYE, not like Uptelnafib, where essentially when it contacts the surface of fats and oils, causes it to what we call render, generates a separation of the glycerin and the fat into what we call soap. So if you ever look online at the soap making process, or if you've ever done soap making yourself, I know there's quite a few crafty folks out there, you will know that adding lye or lye water to a fat or an oil to create a soap generates a lot of heat, and then it separates into a liquid and a solid, kind of like separating curds and whey in cheese making. Thing you have to be careful of is that there are lots of fats and oils on your skin. So if you get contacted by an alkaline chemical, especially one of a certain concentration, it can cause chemical burns to your skin, like in Fight Club. So you always want to be very careful about that. But the good thing is once the soapy foam is generated, it does not burn easily. It tends to just kind of melt and smoke, and it tends to go out very quickly. So, soap versus wax is a very different thing. As far as making candles and making soap, they may come from similar sources. Back in the old days, it would be things like beef tallow, but they burn very, very differently because of the chemical processes used to render them. So something that you are probably going to be a bit more observant of would be things like the MSDS or the material data sheet. I think they call it just an MDS now, for different cleaning supplies. In environments where you need face masks or eye protection, you got to make sure you know how to use it and in what environment it should be employed. So we see here that the higher the number, the more dangerous something is. For a health hazard, going from normal up to extremely deadly for human health. Fire hazard, we see going from a non-flammable substance, increasing in the lowered flash point to where eventually at a level 4, this stuff will spontaneously ignite at what we call room temperature, around 72 degrees. In certain cases, it may be even lower than that for certain really volatile chemicals. So, you know, the more danger involved of, you know, this stuff is exposed to open air. Usually it's got to be kept under a vacuum or sealed liquid container so that way it cannot react and start burning. Specific hazards would be things like oxidizers, acids, alkalins, corrosive agents, radioactive materials. The W with a slash through it is one that I have not seen in a while, but it is for materials that are very reactive with water. So you want to make sure that there is no water exposure for that particular material. Keep it in a dry environment. The stability hazard indicated by the yellow diamond, we go from a stable material up to may detonate spontaneously at level 4. Other than that, is traditionally we have to introduce some kind of catalyst in order to make that change. Now, people can always trip over, you know, things that are left haphazardly about. I know people that'll trip on a tile floor because they're not paying attention. And I don't mean that to be funny. It's just, you know, that tripping and things like that can happen everywhere unless we follow what we talked about just a bit ago of make sure that you're aware of your environment. So we need to reduce that risk wherever possible. If we have cables that cross a floor, let's make sure that said cables are secured. We're providing a relatively smooth surface area that somebody is not going to fall over. Cord covers are a good one. They sell some really inexpensive ones, usually in a coil that you can then trim to length. They're normally like tan or something, very neutral colors. And then you can either just anchor them down, or you can use adhesive strips. In certain cases, you can actually screw them into the floor or nail them in place. Just make sure that, you know, loose cables aren't hanging about, because they'll catch a shoe or shoelace or any number of things. Trip hazards in general are just what we use as a terminology for any cables, cords, or other items in a traffic area that could cause injury. So just, again, be aware of your environment. It's a big, big thing in the lab. Protecting equipment. Important thing to be aware of. Electrostatic discharge, also known as static electricity, or ESD. Now, I have included in this particular slide an example of very aggressive ESD, to where you actually see the surface of the contacts, the board, and the chip have all experienced very dramatic discharges of electricity. So you can see just kind of to the right of the center of where the three things have kind of converged, the model number, and it's a Phillips chip, but right there you can see that there's 2 or 3 points at which the discharge occurred, going from 3 separate areas passing electricity into the chip. Enough so to where it started to expand and ripple outwards and cause these char marks. I've included the basic thresholds, the average levels at which different types of damage occurs. So visible discharge of static electricity occurs at around 8,000 volts or 8 kilovolts. Audible discharge, meaning that you hear the pop. Visible discharge, where you actually see the spark. Audible is where you hear the pop, and that's about 6,000 volts, 6 kilovolts. Tactile discharge, where we can actually feel it. Human beings would be like, ah, that little zap, that hurt. 1,500 volts, 1.5 kilovolts. And this is the kicker. Damage to an integrated circuit, like this chip, obviously not quite as visible as this, is only 10 volts. So there's a 150-fold difference between when we would notice and when the computer component would notice. Pretty major changeover. Okay, so just make sure that you're not leaving ESD up to chance. Make sure that when you're working with a particular object that you always follow procedure and use your anti-static straps, mats, and bags, which we will provide in abundance while you're in the lab with us. Another thing I want to talk about here is the difference between an upset failure and a catastrophic failure. An upset failure is where we have something that's just kind of a hiccup. Let's say that we have a power surge and the computer shuts down. Well, we boot it back up, everything's fine. That was a minor incident. That was an inconvenience more than anything. Sometimes it can be that there's very minor damage to something and it starts to degrade, but we have enough time to where we can get everything back up and running, maybe back up the data from a hard drive that's been damaged or something similar. We can recover though, pretty simple. Catastrophic failure, on the other hand, is exactly what the name implies. Excuse me. Game over. Catastrophic failure means that the game is done because whatever this component is cannot be salvaged. Upset failures you can recover from, catastrophic failures you cannot. So when we're dealing with ESD, not only do we want to use our protective equipment, but we want to be aware of other things in the environment as well. If we're passing sensitive components from one person to another, make sure you ground yourself and then touch the other person before you complete the pass. Usually what I recommend is the elbow bump. It tends to work fairly well. Leave components in their ASBs or anti-static bags until they are ready to use. Work on hard floors or prepared carpets to prevent buildup of static electricity. Also make sure you wear appropriate clothing. So, closed-toed shoes, that's a big difference. Wearing sandals and things like that in the lab just not only increases potential tripping hazards, but often doesn't have very good grounding properties. Avoid working in cold and dry environments. These are areas in which static is very prominent and very easy to generate. Remove packing tape and cellophane from work areas quickly because they're able to generate a lot of static. As I'm sure you guys have experienced throughout your lives, packing tape, clear packing tape tends to be very sticky and it tends to, cling to everything. And shrink wrap, that's what cellophane is, does the same thing. Packing peanuts also have a lot of cling to them. So that static buildup, that static cling is really dangerous around components. So if you ever notice, whenever something is shipped to you, as far as a computer component goes, generally it's in an outer box, then there's like padding, and then there's an inner box, and the inner box usually has like a shaped cardboard or not like paper mache, but I'm trying to think of what you'd call it. It's just kind of a rough cardboard, if you will, framework around it, and then an anti-static bag around the component. And this is because they know that during the shipping process there's lots of rubbing and moving of these textile products that could generate static. So they have to make sure that stuff that is shipped through the mail or through UPS or other ground transport is going to be secured. You also want to make sure that these components are kept away from hair and clothing. So I don't recommend that you wear like a kind of a blousy sweater or anything that's really loose or might drag across components. If you have long hair, again, make sure it's tied back. Don't try and balance a video card on your head or anything like that. You want to try and make sure that any potentially high static environment be minimized as much as possible. We got to protect equipment as well. We have to make sure that any environment in which there may be smoke, dust, or other contaminants, we provide plastic covers for keyboards, monitors, cases, air filters if possible. A lot of times in warehouses and things like that, you'll see that there are these little pop-up offices, just these little, it's usually just plexiglass and plyboard that are bolted up in order to provide an enclosed space in which dust is unlikely to penetrate, at least not with the same level of density, if you will. Compressed air and anti-static vacuums are very useful. Be aware that these can generate, anti-static obviously can, but compressed air in certain situations can actually generate potentially more static, which could cause damage, so we always want to be very careful about the environments in which we use that. Have good ventilation where possible, always. Avoid high temperatures and humidity. Hard drives have a little, what they call a breather hole, magnetic drives anyway. And in areas where we go from a very high temperature to a very low temperature, or very high humidity to a very low humidity, condensation and changes in air pressure could cause condensation inside of the case, the chassis for that particular drive, which when we get into the hard drives chapter, we'll revisit, but could possibly cause skipping damage or other corruption of data inside the machine. Always make sure, of course, that you're using surge and UPS protection as well. UPS standing for uninterruptible power supply. It's able to continuously deliver power from a battery source in the event of the mains being cut off. And of course, surge protection being important to make sure that your devices don't get cooked in the event of a spike in voltage or amperage. Then, of course, we have to worry about protecting the environment. It's an important aspect of being a responsible technologist, being involved in IT or programming or whatever else you do. Whenever we retire technology, we have to make sure that we do so responsibly and ethically. What is the best possible method? So let's look at some different parts that we might see. Alkaline batteries, just a standard copper top. You go buy some Rayovac AAAs or whatever else, and then they run out. let's go ahead and make sure that if we can, we recycle them. Recycling batteries allows us to reuse some of the more sensitive materials, so that way we don't have to mine fresh all the time, constantly do strip mining or other aggressive items. It also keeps the lead acid that is sometimes used for those types of batteries from getting into groundwater, to keep them from going into regular trash. Lithium-ion batteries, mercury-based batteries, silver oxide, nickel cadmium, rechargeables essentially. These are batteries that you need to return to a dealer or recycle via a local recycling center, county disposal, e-waste delivery at various big name retailers, places like Target and Best Buy. They have a recycling bin up front for electronics more often than not. Do not dispose of these in the regular trash, as they are considered toxic waste. If these things leach into the groundwater, where do they accumulate? The food chain, which the food chain in most places, we're at the top, so everything ends up coming back into us. So, you know, bone weakness and birth defects, things like that, let's avoid it by being responsible. Cell phones and tablets contain a lot of rare earth metals and other precious components that can be recycled or refurbished pretty easily by most large retailers. So cell phone carriers, electronics retailers are going to have recycle bins for e-waste of that type as well. If you have a functional device, you can occasionally donate these to charity and domestic violence shelters to allow people who are in potentially hazardous situations to have a means of contact that is not limited by a potentially abusive partner or things of that kind of kidney. You can also visit websites like ecocell.com and be able to resell your device depending on its age and viability. Laser printer toner cartridges, you want to make sure that these are returned to the manufacturer for recycling. These can be very dangerous as they contribute to microplastics in water and the rest of the environment. The good thing is when you buy a new toner cartridge, for the majority, actually it may be something that's required by law now, there is a baggie that is included that's postage paid. You just put your old container in it and you ship it to the manufacturer, and they can go ahead and take that in. And this is beneficial for them too, because there is usually some toner left in the cartridge which they can retrieve and then use for refurbished cartridges. They can use the casing for refurbished cartridges to be able to be sold at a lower price, and it prevents those hazardous materials, as I said, from going into the water supply or into the local environment. Storage media, and this is storage media of all kinds, so hard disks, CDs, DVDs, Blu-rays. Depending on your organization, you'll want to physically damage the items to prevent data recovery and then recycle them. Recycling is preferred, of course. Trash if, you know, there's no recycling option available. Inkjet cartridges, PC cases, monitors, solvents, power supplies, other parts. These are all items that you're probably going to have to check your local agency for proper disposal. So in our case here in Wilmington, you know, contact New Hanover County Waste Management and be like, hey, I've got, you know, 5 or 6 old school tube TVs or old school monitors or PC cases or things like that I need to get rid of. You know, where do I take them in order to be safely recycled or taken care of? And they'll walk you through the process. E-waste is actually a very profitable industry. There's a lot of money in recovering, again, like I said, some of these rare earth metals. I believe something like 80% of the elements on the periodic table that are non-radioactive are included in an iPhone, I think an iPhone X, whatever it is. So, you know, it's even traces of them are present. So it's amazing what's involved in your cell phone, etc. So just make sure that you take care of these things in a responsible way. And that is the end of Appendix A. Thank you for listening, and I'll see you again next time.